Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss Fourier integral theorem. Let's begin. Basically, integral theorems or integral transformations are used when we found out the solutions of partial differential equations. There are various kinds of integral transformations. According to your syllabus, we discuss about two types of integral transformation. One is Fourier transformation and another one is Laplace transformations. In that particular video, we discuss Fourier integral theorem. Statement: a function f of x which is piecewise continuous on every finite interval, the closed interval minus L to plus L, and that one is absolutely integrable on the x axis. Then that function can be represented by Fourier integral. The condition for a given function to be represented by Fourier integral, that given function is piecewise continuous on every finite interval and it is absolutely integrable on x axis, then that is represented by Fourier integral, and that given function f of x in terms of Fourier integral is equal to f of x is equal to integration over 0 to infinite a omega cos omega x plus b omega sin omega x with respect to d omega we integrate, whereas a omega is equal to 1 by pi integration over minus infinity to plus infinity f of t cos omega t dt, and b as a function of omega 1 by pi minus infinity to plus infinity f of t sin omega t dt. Now we have to prove Fourier integral theorem. Proof of Fourier integral theorem. We studied about Fourier transformations, Fourier series expansions. Fourier series expansions we have already discussed in mathematical physics paper 2. So, you know that the Fourier series expansion of, let that given function f of x in the interval closed interval minus L to plus L is given by f of x is equal to a naught by 2 plus summation over n is equal to 1 to infinity a n cos n pi x divided by L plus b n sin n pi x divided by L. This is the Fourier series expansion of that given function. Equation number 1. Where a n, b n, a naught are the Fourier coefficients, where a naught is equal to 1 by two L integration over 1 by L minus L to plus L f of t dt. Another Fourier coefficient a n is equal to 1 by L integration over minus L to L f of t cos n pi t L dt. Another coefficient b n 1 by L integration over minus L to plus L f of t sin n pi t divided by L dt. A naught a n b n a naught a n b n are Fourier coefficient. Let me put these values in equation 1. Putting the values of a naught, a n and b n in equation 1, we get the given function f of x is equal to value of a naught is put it, so the expression will be 1 by 2L integration over minus L to plus L f of t dt plus inside that of summation we put the value of a n and b n in these two terms 1 by L summation over n is equal to 1 to infinity a n values as put it f of t cos n pi t divided by L dt integration over minus L to plus L f of t cos n pi t divided by L dt. Next, cos n pi x by L, cos n pi x by L plus value of b n is put it, so 1 by L summation over n is equal to 1 to infinity integration over minus L to plus L f of t sin n pi t by L dt into sin n pi x by L, sin n pi x by L. Now, we rearranging the terms in these two terms, we have to take common as 1 by L f of t. The given function f of x is equal to 1 by 2L integration over minus L to L f of t dt plus 1 by L summation over n from 1 to infinity integration from minus L to plus L f of t. Inside that bracket the terms are cos n pi t by L into cos n pi x by L plus sin n pi t by L into sin n pi x by L. The formula like cos A cos B plus sin A sin B, that is cos of A minus B. Or f of x is equal to 1 by 2L minus L to plus L f of t dt plus 1 by L summation over n is equal to 1 to infinity f of t integration from minus L to plus L cos A minus B or n pi t minus x divided by L dt. Here dt will be there in that of integration. Equation number 2. Here we prefer a substitution. What is the substitution? Let us substitute omega is equal to n pi by L. Then delta omega, omega of n plus 1 to omega of nth n plus 1 term, the change in omega. Here n plus 1 pi divided by L minus n pi divided by L, which implies delta omega is equal to pi by L. These substitutions let be putted in that of expression 2. Hence, equation 2 becomes f of x is equal to 1 divided by 2L minus L to plus L f of t dt plus 1 by pi summation over n is equal to 1 to infinity integration over minus L to plus L f of t cos omega t minus x dt del omega. Equation number 3. These substitutions are putted in equation number 2. Here, but when L tends to infinity, 1 by L definitely tends to 0. Also delta omega, which is pi by L, that is 1 by L tends to 0. So pi by L also tends to 0. That's why the infinite series of that of given equation, infinite series, that is n is equal to 1 to infinity, can be transformed into integral form, that from 0 to infinity. Then the infinite series in equation becomes an integral from 0 to infinity. Equation 3 reduces to f of x is equal to 1 by pi integration over 0 to infinity, integration over minus infinity to plus infinity, f of t cos omega t minus x dt in d omega. Or use cos a minus b formula, f of x is equal to 1 by pi integration from 0 to infinity, integration from minus infinity to plus infinity, f of t cos omega t dt cos omega x d omega plus 1 by pi 0 to infinity minus infinity to plus infinity f of t sin omega t dt sin omega x d omega cos a minus b, cos a cos b plus sin a sin b. And equation number 4. Let we introduce the coefficients as so. If we introduce the integral 1 by pi minus infinity to plus infinity f of t cos omega t dt, that integral as a omega is equal to 1 by pi minus infinity to plus infinity f of t cos omega t dt and b omega as the integral 1 by pi minus infinity to plus infinity f of t cos omega t dt. These two substitutions are introduced. The equation 4 written as, then equation 4 written as the given function f of x is equal to integration from 0 to infinity a omega cos omega x plus b as a function of omega sin omega x of d omega, a as a function of omega, b as a function of omega. that given expression is the Fourier integral of that given function, which is known as Fourier integral of the given function f of x. Fourier integral of given function f of x. That one is our statement, that is the Fourier integral. We prove the Fourier integral by taking Fourier series expansion. Next, look at that expression. When we put, if that function is either even or odd, that can be classified as, if f of x is an even function, then b of omega will be 0. For even function, that integral will be 0. Look here, if f of x is an even function, then b of omega is equal to 0. For even function, that integral will be 0, but a of omega exists, but a as a function of omega will be how much? 1 by pi minus infinity to plus infinity f of t cos omega t dt. But when take the limit from 0 to infinity, 2 is multiplied, so a omega is written as 2 by pi integration over 0 to infinity f of t cos omega t dt. As the limit from 0 to infinity, a 2 is multiplied. Here is the limit from minus infinity to plus infinity, that is limit from 0 to infinity. As we take 0 to infinity, so 2 is multiplied. Then the Fourier transform, Fourier integral, then Fourier integral becomes f of x is equal to 0 to infinity only due to the contribution of cos omega x d omega. Here there will be the cos term. That is the reason we say it as Fourier cosine integral, which is Fourier cosine integral. Fourier cosine integral. Next, alternatively, if the given function is an odd one, then what happened that case? If f of x is an odd function, then a of omega will be 0. For odd one, that integral will be, that constant term will be 0. But a of b of omega have the value 2 by pi as the limit from 0 to infinity f of t sin omega t dt. F of t, okay, there will be a mistake here, that b term is the sine omega t. Sine omega t. Here is the sine one. Sine omega t. As sine is odd function, cos is the even function. So, the Fourier transform, then Fourier integral becomes f of x is equal to zero to infinity b omega sin omega t dt. This is the contribution due to sine function, which is known as Fourier sine integral, which is Fourier sine integral. Fourier sine integral. From Fourier integral of given function, we say if that given function is even, then it is Fourier cosine integral, and if that function is odd, then it will be the Fourier sine integral. Next, Fourier integral in complex form. How we represent a complex form of Fourier integral? Generally, for even function, of f of x, the Fourier integral is given by f of x is equal to, that is the Fourier cosine integral 0 to infinity a omega cos omega x dx. The value of a omega is put. So, we have 1 by pi 0 to infinity, that from minus infinity to plus infinity cos omega t minus x f of t dt d omega. That equation number 1. Here we use the value of a omega as taking the limit minus infinity to plus infinity, that 2 is omitted. So, it will be 1 by pi minus infinity to plus infinity f of t cos omega t dt. Here we use a substitution omega of t minus x. As cos of omega of t minus x is an even function of omega. So, it will be further written as f of x since the limit from minus infinity to plus infinity 1 2 is divided here, as the limit is 0 to infinity. So, we write half 1 by pi since the limit from minus infinity to plus infinity, here minus infinity to plus infinity f of t cos omega t minus x dt d omega. Equation number 2. Why we transform just like this as cos omega t minus x is an even function. Therefore, we transform the limit minus infinity to plus infinity. Also, for odd function of f of x, it is written as for odd function generally for odd function the limit minus infinity to plus infinity sine omega t minus x dt is equal to 0, as sine omega of t minus x is an odd function. The integral of odd function from minus infinity to plus infinity will be 0. Hence, it can be written like this. If I just multiply I by 2 pi minus infinity to plus infinity minus infinity to plus infinity f of t sine omega t minus x dt d omega will be 0. There will be no such change. I just multiply I by pi integration minus infinity plus infinity f of t dt. Just add equation 2 and 3. Due to that value will be 0. When we add equation 2 with 3, there will be no such change of that given function. Then adding equation 2 and 3, we get f of x is equal to 1 by 2 pi integration from minus infinity to plus infinity minus infinity to plus infinity f of t cos omega t minus x dt d omega plus I by 2 pi minus infinity to plus infinity minus infinity to plus infinity f of t sine omega t minus x here dt d omega, or f of x is equal to 1 by 2 pi minus infinity to plus infinity minus infinity to plus infinity f of t as common in these two terms cos omega t minus x plus I sin omega t minus x dt d omega, or f of x is equal to 1 by 2 pi integration from minus infinity to plus infinity minus infinity to plus infinity f of t, that representation cos theta plus I sin theta in form of e to the power I omega t minus x dt d omega. Therefore f of x is equal to 1 by 2 pi minus infinity to plus infinity minus infinity to plus infinity f of t e to the power I omega t dt. Another integral as e to the power minus I omega x d omega. That is the Fourier integral in complex form. Fourier integral in complex form of that function f of x. Let me take an example to find out Fourier integral transform. To solve various kinds of problems in case of Fourier integral transforms, we have to remember some standard useful results of integrals, as integration over minus infinity to plus infinity e to the power minus x square dx is equal to under root of pi. Integration over 0 to infinity sin ax divided by x of dx is equal to pi by 2, provided that a greater than 0, a is positive. Next, integration over e to the power x cos bx dx is equal to e to the power x divided by a square plus b square whole into a cos bx plus b sin bx. Again, integration over e to the power x sin bx of dx, same thing, e to the power x divided by a square plus b square, here a sin bx minus cos bx. Next, integration over 0 to infinity e to the power minus ax divided by x into sin bx dx is equal to tan inverse b by c. Integration number 3 and 4 are most important. These are very useful to solve various kinds of problems related to integral transforms. A question is given: find the Fourier integral representation of the given function f of x that results 0 when x less than 0, that result e to the power minus x when x greater than 0. How to solve that kind of question? As we know, a of omega, that is 1 by pi integration over minus infinity to plus infinity f of t cos omega t dt, 1 by pi minus infinity to plus infinity can be written as minus infinity to 0, 0 to infinity. So, f of t cos omega t dt plus 0 to infinity f of t cos omega t dt, minus infinity to plus infinity as minus infinity to 0, 0 to plus infinity, 1 by pi. Here minus infinity to plus infinity, that under this category x less than 0. So, here the function will be 0. So, here that results will be 0, only that term exists. Here x greater than 0 as e to the power minus x. So, the integration is 0 to infinity e to the power minus t cos omega t dt, as that value is 0 in that of given region. That kind of integration can be solved by putting this formula. E to the power ax cos bx formula is used. So, the result is equal to 1 by pi e to the power minus t divided by 1 plus omega square minus cos omega t plus omega sin omega t, limit from 0 to infinity. or 1 by pi e to the power minus t divided by 1 plus omega square, that value as 1. Next, b of omega 1 by pi integration over 0 to 1 by pi 0 to infinity that is minus infinity to plus infinity f of t sin omega t dt. Limit is divided as minus infinity to 0 and 0 to plus infinity. So, 1 by pi integration over minus infinity to 0 f of t sin omega t dt plus 1 by pi 0 to infinity f of t sin omega t dt. That integral 0 as f of t as 0, only contribution of that integral. So, b as a function of omega 1 by pi 0 to infinity value of f of t as e minus t, here as a function of x, here as a function of t, e to the power minus t sin omega t dt. We use that standard formula e to the power x sin vx dx. The integral is evaluated just as 1 by pi e to the power minus t divided by 1 plus omega square. Okay, that limit is calculated from 0 to infinity here, that results as e to the power minus t 1 plus omega square minus sin omega t minus omega cos omega t 0 to infinity, here same thing 1 by pi omega divided by 1 plus omega square. Here the evaluated limit one divided 1 plus omega square, its evaluation limit omega divided by 1 plus omega square. Now, Fourier integral transform f of x is equal to 0 to infinity a as a function of omega cos omega x plus b as a function of omega sin omega x with respect to d omega. The values of a omega and b omega is put here. So, 1 by pi integration over 0 to infinity value of a omega 1 divided by 1 plus omega square cos omega x plus value of b omega divided by 1 plus omega square sin omega x. In these two terms 1 by pi as common, that to the outside of that of bracket, of d omega. Under solving it, 1 by pi 0 to infinity 1 divided by 1 plus omega square as common, we have cos omega x plus omega sin omega x over d omega. That is the integral transform of that given function as it is given. F of x is equal to 0 when x less than 0, f of x is equal to e to the power minus x when x greater than 0, and the Fourier integral representation of that given function. So, with the help of this video lecture, we understand what is Fourier integral theorem, the statement and proof of that Fourier integral transform. Fourier integral of that given function f of x, then Fourier cosine integral and Fourier sine integral, complex form of Fourier integral, some standards integrals which is very useful to solving the problems related to Fourier integral. A question given to us, we found out the Fourier integral of that given function, that is the Fourier integral of that given function. So, with this useful and informative notes, let me wind up this session. Thank you.